Great. So let's have the next speaker. So next talk is now also about how to re-optimize collective communications, but now treating it as a multi-commodity flow problem. This talk, let's switch the slides to the next talk. This talk will be presented by Xu-Ting Liu. He's a PhD student at University of Pennsylvania, advised by Professor Vincent Liu. He is interested in building systems for distributed machine learning. Take it.
Thank you.
Just speak here if you want.
Okay, I get this. Hello, everyone. I'm Xu-Ting Liu from University of Pennsylvania. Today, I'm discussing rethinking machine learning collective communication as a multi-commodity flow problem. This is a joint work with Benas, Siva, Liangyu, Vincent, Miguel, Srikant, and Luke. So we all know that machine learning models now are getting larger and larger. So people now have to distribute model and data across multiple GPUs and perhaps in multiple nodes or servers. So the network communication required also grows. So one common scenario for this kinds of communication is when in a data parallel training pipeline, sometimes GPUs want to sync gradients periodically. So in this case, they would perform a collective communication primitive called allGather, where GPUs collect gradients from each other to sync weights. Unfortunately, this kind of collective communication is very inefficient. Data shows that GPUs can spend as much as 20% to 65% of time idle waiting on network communication. So what exactly is this collective communication that causes this bottleneck? There are many kinds of collective communication primitives. Each of them specifies what each node wants to send, which will start at its input buffer, and what this node wants to receive, which would end up at its output buffer. Let's take allGather as an example. In allGather, each node wants to share one chunk of data to everyone else. So at the beginning, before allGather, all the nodes start with one chunk. And after allGather, all the node now has one chunk from every other node. So this can also be expressed in this form of demand matrix. So the first row tells us node 1 wants a chunk from node 2, node 3, and node 4, and so on. Now, what does a collective communication scheduler do? A scheduler's job is to do some offline planning and will give us a communication schedule such that by following this communication schedule, we can finish our collective communication. This communication schedule will determine link utilization or queuing, and ultimately, it determines how fast to complete a collective communication. Let's take this simple ring schedule as an example. So a ring schedule will tell each node to send one chunk to its immediate neighbor in every epoch. For the first epoch, node 1 will send the light blue chunk to node 2, and node 2 will send the yellow chunk to node 3. And they do the same thing for epoch 2 and epoch 3. At the end, after 3 epochs, we finish our allGather collective in this ring schedule. And the total time takes is 3 times alpha plus chunk size divided by bandwidth. This little alpha is link latency. So it's a very important aspect in our later modeling, especially when chunk size is small. So I'd say this is a very elegant schedule. There is no problem like congestion or dependency conflicts. But the problem is some links in this topology is not used at all. So there's wasted bandwidth right here. So people notice this problem and want to improve this. The benefits of this kinds of pure algorithm collective schedule is that they are one size fits all. That means they can be applied to almost all kinds of topologies. And they are widely used in default collective communication libraries from NVIDIA and AMD, Nico and Rico. But they underutilize topology, and there is no data size awareness. So people have been working on to create a more precise mathematical modeling of such communication problem. And they work well with heterogeneous topology, and it gives you a tailored fit schedule that are much better in schedule quality. However, people notice that because this process is simply hard, the time and resources needed to generate such a schedule increases exponentially as the topology grows. And actually, MSQL, for example, cannot scale to multi-nodes topology. But multi-node is the very scenario that we want better schedule. So a second class of approaches falls back on increasingly rough heuristics in order to increase scalability. Heuristic-based schedulers like Taco are much better at scalability. However, their heuristics undermines quality. So in our work, we argue that it is too early to give up upon near-optimal solutions for collective communication, and it is possible to increase scalability without sacrificing performance. Our inspiration that gives us hope that we can do so is from traffic engineering. Traffic engineering has solved a lot of similar problems at the scale we need today. So for traffic engineering, we also have a topology as our input, but now we have data centers instead of GPUs. And in traffic engineering, our input also have a demand matrix telling each node where you want to send or where you want to receive. And we are solving a problem of resource allocation where we are trying to allocate flows onto links to meet such demands while also not exceeding capacity on the links. And even for the objective function, traffic engineering are having a similar objective to maximize utilization or the amount of traffic served or trying to minimize time. And there's tons of advantages of framing the collective communication problem in a traffic engineering way. First, traffic engineering has been studied for decades in networking, so there's years of research we can pull from. And we have been deployed traffic engineering solutions in large production networks. They can scale up to 100 nodes topologies, which is the scale we need for our increasingly large models. And lastly, we know how to solve traffic engineering problems optimally. That means we can potentially get better quality schedules. This leads us to TICO, traffic engineering-based collective communication library. TICO is a traffic engineering-based formulation, and it produces faster collective communication, as fast as 2 times faster than previous state of the art. And TICO can scale to multi-node topologies. In short, TICO proves that it is possible to improve solution quality while also maintaining scalability. So now let's dive deep into how TICO really works. Let's look at how a traditional problem in traffic engineering works. So I've mentioned that there are a lot of similarities, but in fact there are fundamental differences that make a direct application of traffic engineering not possible on collective communication. In traffic engineering, our problem looks like this. Our inputs include nodes, edges, and the demand matrix, and we are trying to find some assignment of flows onto the edges in order to maximize the objective. And we are doing this while ensuring all the assignments are feasible by conforming to capacity constraints, which is you cannot exceed capacity on any links. This makes sure that this network or the schedule doesn't have any congestion. And the second constraint is flow conservation constraints. This makes sure that this network does not magically create or lose traffic anywhere. And there are 4 important changes to make to this formulation in order to adapt it to collective communication. They are latency and queuing, in-network copies, discretized sends, and support for storage and caching. And I will be focusing on first 3 in this talk. So first, there's a recap about all-to-all collective. It is actually very similar to all-gather, but now each node wants a distinct chunk from every other node, so your input buffer now has much more data compared to the all-gather we saw earlier. The reason I used all-to-all here is one can notice it is very similar to the demand matrix of a traffic engineering's demand matrix, and one may say this D21 is just C21. They are meaning the same thing. But actually, are they the same thing? The answer is, of course, no, they are not the same thing. So in traffic engineering, demand here is a stream of traffic. So D21 means that node 1 wants a stream of traffic D21 from node 2. On the other hand, for collective communication, C21 means that node 1 wants a chunk C21 from node 2. So a fundamental difference between the two is that it's a chunk versus traffic, where a chunk is a fixed amount of data, while in traffic engineering, we are dealing with an infinite amount of data in the form of a stream of traffic. This differences has many implications in the 4 changes that I'm going to discuss. So first, one of the implications it leads to is when we are trying to add precise delay to traffic engineering, because traffic engineering makes fluid flow approximation as demands are fixed and sustained. Now the demand is simply the maximum end-to-end transfer time across all paths. So on this topology, source 1 and source 2 are both trying to send this chunk to the destination. So and all the links over here have the same bandwidth, so they can send one chunk in 1 second. So the bandwidth is the same, but they are having a different alpha delay. Alpha is the link latency. So in traditional traffic engineering, we just estimate our delay by comparing the maximum of source 1 and destination and source 2 and destination. So we can just simply add all those alpha up and add the bandwidth time up, and we can find they are having the same time. So the delay is the same, 3 alpha 1 plus 4 for both paths. And our traffic engineering estimation, delay estimation is 3 alpha 1 plus 4. But when we take a closer look, we find out this estimation to be inaccurate if we are sending chunks instead of a stream of traffic. So the blue chunk and light blue chunk and dark blue chunk will in fact arrive at node H3 at the same time. And now one chunk has to wait for the other chunk. This queuing increases our delay estimation by 1 second. So this 1 second seems to be very, very small, but this has a rippling effect in our schedule, and it's quite important as small chunks are quite popular in our collective communication. In order to add such accurate estimation to our formulation, we have to modify our flow conservation constraints. So for our original flow conservation constraints, on the left-hand side, we have the flow that comes in at time k, and plus what's in the buffer at time k. That would be equal to what's in the buffer at time k plus 1, plus the flow that goes out at k plus 1. So that's our original formulation. In order to account for this alpha delay, we now calculate delta, which is number of epochs a chunk needs to traverse a link, and that is dependent on alpha. So we account for this delta time to change our formulation to the flow that comes in by time k, and this will give us a better formulation of alpha in our formulation. And second, we need to model copy. This is a very simple topology that source wants to send this chunk to 3 destinations. With copy enabled, we can simply complete this schedule in just 2 steps if node edge can copy the chunks to three more chunks. But we can notice that the traditional flow conservation constraints don't hold here because incoming data doesn't equal to outgoing data. So we need to change that in order to support copy. So we need to again modify our flow conservation constraints. So on the left-hand side, we have what's in the buffer at time k, and plus the flow that comes in by time c. That will be greater than or equals to the maximum of the flow that goes out on each link in time k plus 1. So this gives us a modified flow conservation constraints that supports copy. And third, there's another problem that we need to track each chunk in the network. So if in the traditional traffic engineering, there's no sense of chunk or because it's all a stream of data. But now, if we allow node 1 to split one chunk into 2 chunks for various reasons, now these 2 chunks both want to go to node 4. And it is very possible that the first chunk gets sent twice to node 4. And node 4 will think that all the optimization constraints are satisfied. I have received all the amount of data I want. But in fact, you just received the same chunk twice. And that's not what we want for our collective communication. In order to fix this problem, we have to use integer variables. So we do not allow chunks to be split in the network. And we can change out the number of chunks during problem setup in order to treat this optimization of number of chunks and our quality schedule. So this is our modified flow conservation constraints, where we are accounting for the chunk everywhere in order to track the chunks in our network. There are more details in our paper, including how we formulate our problem into a mixed integer linear program, or a linear program, or an A-star program, which further increases our scalability by giving rewards in every turn when you move closer to your destination. For our evaluation, we compare performance against TACO and RICO. We are comparing solution quality as well as solver speed, and we ran large-scale simulations and hardware experiments. So we are doing an OGATher and OTO with commodity topologies and our internal topologies up to 256 GPUs. For our solver quality, the y-axis is our improvement over TACO, previous state-of-the-art, and x-axis is our output buffer size, basically the data size to transfer. So TACO performs the best when there are more chassis, when the topology is larger, and it performs this with OTO architecture, probably because OTO is more natural to traffic engineering. And we are also having better scalabilities to solve a solution for 256 GPUs in just 2.8 hours, and that's a very fast time compared to TACO. And for our hardware results, we are beating TACO and RICO, and we see a spike here probably because this is a sweet spot where neither alpha nor the bandwidth time dominates our formulation. And our challenges and future directions includes how to better lower to hardware, how to handle failures, and supporting for other collectives, including all reduce. In conclusion, TACO modifies traditional traffic engineering to formulate the collective communication problem, and TACO achieves better scalability and solution quality. Our code is available on GitHub, and please come and try our code. Thank you.
Hi, thanks for a great talk. This is Ke Liu from Huawei, the computing product line. I've got a question about, as you mentioned in your last page, that you only compares performance of the OGATher and OTO, which does not require does not have the dependency between chunks. So what is the challenge of your solution to work on with the OHUs or reduce scatter or gather?
Yes, thanks for the question. So for other collectives like OReduce, you can technically use our formulation to, you can use our existing schedule of OGATher to and OReduce can be constructed, for example, by combining a reduced scatter and a OGATher, and you can get a schedule of reduced scatter by reversing R of OGATher. So it is possible to construct a schedule that way. While it is also possible to use the formulation and model OReduce directly, and we think it is possible, but we haven't done so in our paper.
Okay, looking forward for your future work.
Thank you.
Yeah, hi, Xuting. Thank you for your great talk. So I'm Jingyi from Huawei, and I have two questions for you. The first one is that does your solution require synchronization between different GPUs, and how do you tackle the jitter caused by the difference of computation capacity of different GPUs? And the second question is, does your solution apply to math tasks, like the problem solved by the previous paper?
Hi, yeah, thanks for the question. For the first question, yes, so we do not require synchronization between GPUs. So we compute our schedule offline, and we give the schedule to all the GPUs, and we hope they can complete their task on time. When jitters comes and that task comes, there will be decrease in our performance, and we have noticed that. So that's also a future work to work on. And for the second question, do you mind repeat that?
Yeah, so does this solution apply to multitasks and multiple jobs?
Yes, for multi-tenancy, yes, I'd say it's a strength of traffic engineering that traffic engineering supports multi-tenancy nicely. So it is possible to model multi-tenant workload into our formulation. And I think it's a good direction to work on in the future to better improve this formulation.
Okay, thank you.
Thank you.
One last short question.
Okay. Very good talk. I'm Kun Qian from Alibaba Cloud. In your paper, it is you propose a new formulation inspired by the traffic engineering and help you solve the collective communication problem. So actually, in the implementation, you still use the ILP, linear programming, or
Yes.
something to solve it. So actually, it is the same method in TACO or MCCO.
Yes.
So why the new formulation? The basic insight is what to let the new formulation help you shrink the solution space to help you better conquer the multi-node problem.
Yes, thanks for the question. So I think the magic comes from the field of traffic engineering, where this traffic engineering formulation has been studied and optimized for decades. So our formulation based on traffic engineering formulation turns out to be better in efficiency and schedule quality than previous formulations. And we also design other formulations, including A-star, which further increases the scalability compared to those MILP or ALP problem.
Okay, thank you.
Thank you.
Let's thank the speakers again.